means I probably won't get terribly far, and I'm really going to talk about rather basic things. So I think later on in this school I've noticed a lot of sort of exciting looking titles about things like spectral problem in ESCFT and quantum spectral curves and all sorts of stuff like that. And I'm going to talk about much simpler things. So I'm just going to talk about sort of old-fashioned stuff, what quantum integrability, integral quantum field theories looked like before all these string theories came along, and had lots of other clever ideas. But perhaps it's useful background anyway. And those of you who've seen it all before, well, sorry about that. Yeah, I had a rough plan. I think I won't actually write it on the board because I'm not sure I'm going to get through it. I'm going to start off by today by trying to do a rather simple example of why 1 plus 1 dimensions is rather special. Okay, so some people here may have seen me do this for example already. But it does sort of throw out some amusing structures. So I'll talk about that a bit. But perhaps it also helps to answer one of the questions at the end of the last lecture about why things like beta ansatz work. There's something rather special about one spatial dimension which makes lots of stuff work. But in some sense, all these recent string developments is kind of slightly cheating. You end up studying the same problems using 1 plus 1 dimensional techniques. We can have a long argument about that over beer at some point, perhaps. And then I want to talk about the role of conservation laws. So that'll probably be tomorrow. And these are basic ideas of factorizability in Yang-Baxter equation from the point of view of someone doing quantum field theory. So perhaps in John Sebastian's talk, well, we're already seeing it in the context of things like spin chains, but from the quantum field theory point of view, we'll look at that. And then there's some basic little building blocks from there, things like the two-particle S matrix. I'm afraid I'm going to have to talk a little bit about that. Some of that is very standard. So I might skip some of that on the grounds you can find other places to talk about more exciting things. In the end, I'd quite like to talk, if there's time, about things called bootstrap equations, which don't get quite so much mention nowadays as they used to. They were the focus of a lot of attention before, because there's some rather nice structure there too. So I had time to talk about what's going on with things called bootstrap equations, which are essentially to do with analysing the structure of bound states in the theory. And again, you can get to some quite nice and amusing mathematics there. And I might look at those via some examples that I'm very fond of, which are things called affine total field theories. There's time to talk about those. And in some ways nowadays, well, some of these subjects are slightly coming back. And I think, in a way, the old work scratched at the very simple side of these theories. It turns out they're a lot more complicated than you might think. And so, it's good to look at them from a simple-minded point of view first. So maybe I'll give some references first. So there's some nice lectures. These are all rather old, in line with the content of my lectures. But there's some nice lectures by Saleur, which you can find. They were before the databases turned into the archive. So it's Con 9812110 and 000730309. And so they're called lectures on non-perturbative field theory and quantum impurity problems 1 and 2. Okay. Then there's some lectures with the same title as this course by me, and you'll find rather a lot of resemblance between what I'm saying, at least in the first lecture or two, and these notes. And those are also on the old style archive, so that's 9810026. And, well, there's a very old physics report by Giuseppe Rosado. That's probably quite enough for references. Okay, so what we're going to be doing is we're going to be looking at massive and relativistic quantum field theories in 1 plus 1 dimensions. Okay, so lots of interest nowadays in theories that are either not massive or not relativistic, at least in terms of their special relations. I'm not going to talk about those. And many of them are usefully considered actually some sort of deformations. We've been hearing about high-dimensional conformal field theories before, but these are quite often considered. So we're looking at massive relativistic EFT, but they're often rather explicitly deformations or perturbations of two-dimensional CFTs. Okay, so you call them perturbed conformal field theory. And in 2 dimensions, as you're all pretty well aware, I think, there are all sorts of special properties and extra symmetries and so on, which means that you can pretty much solve completely. And one of the nice discoveries that was made back now about 20 years or so, a bit more, was that some of this solvability lasts even when you make the theory massive. Okay, so what happens is that all this nice conformal symmetry disappears, but actually sort of hidden inside that conformal symmetry, there's an infinite set of commuting quantities which remain conserved even after you've destroyed the conformal symmetry. Okay, and lots and lots of techniques have to do with solving those theories, but in particular, one thing that you can find exactly is an S matrix of these theories often, and that's what we'll be talking about. Okay. And Saturn's analogic is one of the key people who looked at that. So that's a bit of the background. Then we'll start off with my favourite little toy calculation. So section 1 is what's special about 1 plus 1 dimensions? What's special about scattering theories in 1 plus 1 dimensions? I'll go through this all simply. So it's a very simple-minded calculation. On the other hand, if you wanted to sort of see elegantly what was going on and how it would generalise to other cases, so I think you already get onto problems which haven't been addressed properly. So there are sort of interesting homework problems all the way through. I think what I'll do is I'll sort of occasionally I'll write exercise if there's something which is useful for you to check. If I write a star above the exercise, it means it's a bit hard, so you can think about it. It might even be not solved, but it'll give you a little challenge for you. Okay? And not solved might be just because no one's found it interesting enough to solve it. It's just my personal bias. It's an interesting thing to look at. So it doesn't necessarily mean it's too hard to do. Okay, so what I'm going to do is, and at the end of this, actually, although the calculation looked rather simple, at the end of it, we'll get a little physics proof of a theorem about the possibilities for the simplest possible integrable models in 1 plus 1 dimension, which I don't know any other way to really prove in a nice way. So, by doing simple-minded arguments, we'll arrive at a relatively interesting conclusion. So I'm going to start off by looking at what's really the simplest interacting 1 plus 1 dimensional theory you can think of. So it's going to be lambda phi 4 theory in 1 plus 1 dimensions. Okay, so we could write down simple Lagrangian for that, half d phi squared minus half m squared phi squared minus lambda 4 factorial times the fourth. So we'll have a propagator, which would be some suitable set of conventions. I over p squared minus n squared plus I epsilon. The I epsilon will play a role at some point, and there's just one vertex, which will, again, in some set of notations, be minus I lambda. Okay. What I want to do is just examine whether this production amplitudes for this theory. So you might have heard that in 1 plus 1 dimensions, one of the features of integrability is that you don't tend to produce particles. Okay? If you crash particles together in a realistic field theory, then if you crash them together hard enough, you'll produce all sorts of junk. And of course, that's one of the impediments to finding an exact S matrix, because the structure is very complicated, because each time the energy becomes big enough to produce more particles, something changes. You'll get some sort of threshold, some sort of cuts, and all the rest of it. If you had a theory where this didn't happen, well, the S matrix would have a much simpler analytic structure. We'll look at that analytic structure a bit more tomorrow, probably. But for today, let's see just where this might come from in perturbation theory. Okay, so what we want to do, what's the task, is to find the 2 to 4 connected production amplitude at tree levels. So that's a classical calculation. Of course, it's vanishing with hint of classical integrability. When we get started, we've got many more to it than that. So, there's 4 gadgets going out. Okay. It's going to be slightly easier to count the diagrams. I mean, it's not too hard. It's not like doing a proper gauge theory or anything, but it's slightly easier to count the diagram if I turn one of my out momentum into an in momentum, called crossing. And I'll first look at 3 to 3 processes. Okay, just, at least for me, makes it a bit easy to add everything up. But any Feynman diagram you draw for a 3 to 3 process, if you turn one of the outgoing momentum into an ingoing momentum, it's going to give you, in a one-to-one fashion, a Feynman diagram for a 2 to 4 process. So There's subtleties with that continuation which we'll mention later, but at the moment we'll consider that. Okay, so we'll, or 3 to 3 with 1 out, 1, which way around, 1 in, cross, 2 out, later. Okay, so now I've got 3 momentary wave in state, P, say, PA, PB, PC. Now so I've got PD, PD, and PF. Okay, and as a function of those, where of course they also satisfy overall momentum conservation, I want to find out what that amplitude is, what's going on. Okay, I'll use light cone. It's another reason why 1 plus 1 is special. It's rather easy to solve after all the light cone. Of course, in higher dimensions nowadays, at least for massless particles, there are all these cunning techniques for doing it too. In 1 dimension, 1 plus 1 dimensions, you don't really need to think. We'll write momentum as P bar with P bar equals m squared. So P is P0 plus P1, P bar is P0 minus P1. And then we'll solve that by setting, let's say, PA to be N, A, and then N, A inverse, and so on. Okay, PB is N times B inverse, and so on, where A, so for the 3 to 3, A, B, up to F are all positive real. Okay, and then to cross from this 3 to 3 to a 2 to 4, we'll just have to switch, let's say, C to minus C. And we'll get 2 to 4 by sending C to minus C. Okay? Right. Good, so now I'm just going to add up the diagrams. Let's do it. So far, nothing clever at all. And they're just 2 classes of diagram. Okay. So the first class of diagram, if you think about it, so I've just got to plug together my 5, 4 vertices in such a way to join up the 3 incoming to the 3 outgoing. So I've got A, B, and C, D, E, and F. And the momentum there is A plus B minus D, 1 over A plus 1 over B minus 1 over D. Okay, I just conserve momentum at the vertex. Okay, left and right like momentum. That tells me what the momentum in that propagator is. So the internal propagator gives us, so I over P squared minus M squared, which is I over M squared times 1 over A plus B minus D times 1 over A plus 1 over B minus 1 over D minus 1, which is I over N squared minus A times B times D, multiplied A plus B, A minus D, B minus D. You do the outer work. Okay? Good. I ignored the I epsilon. Well, that was kind of naughty of me, but secretly, so the I epsilon only really matters in any of these guys when P squared has a risk of being equal to M squared. Okay, but it's almost on shell. Then it makes a difference. It tells you sort of which direction you've got to continue the amplitude. Okay, but in this case, I'm secretly aiming at calculating the 2 to 4 amplitude, and for that, it's not too hard to check that P squared is never equal to M squared. Okay, that doesn't kind of fit together properly. Okay, so it's okay for the sum things that we'll talk about later. It's sort of interesting as well understanding how these amplitudes behave the way that they do. Okay, that's the first class of diagrams, and obviously I can do permutations of A, B, and C, and D, E, and F, and get some more diagrams, but they're all going to have the same style. Next trick. Brown as well. Right. So if you think about it, there's only one other option that I could have, which I'll call D, sorry, class B, which looks like this. So A, B, and C, B, and F. Okay. Now sitting here, I've got left and right components A plus B plus C. 1 over A plus 1 over B plus 1 over C. Okay, moving forward. And I divided by P squared minus M squared is equal to I over M squared times ABC over A plus B, B plus C, C plus A. Okay, so we're playing around with very elementary functions here. Nothing at all fancy. So, add all that, what do we get? So, it's going to be some sort of overall piece. Okay, but the bit that's different between the so there'll be factors on the legs and all the rest of it, with the soup and all that. Let's call it a constant. But there'll be some overall piece, but then the bits which are different between the different diagrams are just coming from whether I insert this propagator here or this one here. And this one here comes in the various different flavours depending on where A, B, C, and D, E, F are sitting. So it's something times the factor of minus I lambda squared over M squared, so I'm including now the lambdas on each vertex, times some number which I'll call H, which depends on all 6 components of these parameters. H, A, B, C, D, E, F. Alright, and that H is given, that's from the things I wrote down before. It'd be easier to be using one of these fancy pads that Sebastian had. So H of A, B, C, D, E, F is, well, first of all, I've got to do all the A-class diagrams, so the cyclic permutations of A, B, C, and the same of D, E, F, of minus A, B, D divided by A plus B. What was it? A minus D. B minus D. Okay, so that's all the A diagrams. I mean, there's only one B diagram, A, B, C, over A plus B, B plus C, C plus A. Okay, so this is where, you know, all these worries about combinatorial factors when you're doing Feynman diagrams and all the rest of it, you have to get them right, because the final answer is going to be nice, but it's only right when you get them right, you get the factors right. So, of course, if you're doing a real-world calculation, you don't have this to rest on. Anyway, sometimes life's easier for integrable people. Okay, so the overall constant's kind of going to be the same, but we're going to add in the contributions of the two different diagrams, with the correct proportionality factors and so on, with those contributions like that. So finally, we're going to get to something interesting, something surprising, which is, so fact, which you can check, is, so at the moment this is a function of 6 variables, right? 6 real or even complex variables, but if A plus B plus C is equal to D plus E plus F, and 1 over A plus 1 over B plus 1 over C is equal to 1 over D plus 1 over E plus 1 over F. Okay, so 2 constraints, but we've still got quite a big sort of shape of possible values of, well, I've now got 4 parameters left. So in principle H should be something still quite complicated. Then H of A, B, C, D, E, F is identically equal to -1. Okay? So you can check that, you can bug it on a computer and check, or I suppose the exercise, perhaps with a small star, is to find and tell me a nice proof of it. Okay, that's a little challenge to try and sort of figure out why that could be. But anyway, it's one of these sort of curious mathematical facts that integrability keeps on throwing at these funny behaviours happen. Of course, they have to happen because we want the problems to have nice answers. No, but I mean, you can look at the. I've seen things written where you can sort of look at the polls and so on and try to figure it out. It's not massively nice. I don't know anything. I just, when I was first of all checking that I got my combinatorial factors right, I just put it on maple and checked. I'm going to run out of white chalk. Oh no, take it all back. But yeah, it's sort of intriguing. In fact, following from this, I mean, well, I'll mention this maybe in a minute, but there should be a whole string of such identities making these theories work. And where I spoke about this a long time ago, John Bernard, Zuber got kind of interested in discussing it from here, but we never really had a satisfying big picture for it. So that's a sort of bigger scale exercise to see what's further. Okay, anyway, once that's true, does anyone recognise what are these two conditions here? Anyone spot? Perfect. Okay, so they're just the conservation of left and right like co-momentum, which we know has to be true. Okay, I didn't write it down explicitly, but at each vertex here, so at the moment, say for this, I just use conservation here, but there's conservation here as well, and this gives us overall conservation in the whole diagram. So for any amplitude, those two conditions hold. Okay? So therefore, when I'm putting this into an amplitude, rather than writing that h down, I could just write down -1, and I get the right answer. Okay, independently of the rapidities that are coming in, which is kind of cute. Okay, so these are just conservation of left and right. Like cone. These being those conditions there. Okay? And they clearly work. It doesn't matter what, I didn't say anything, well, maybe it's not totally obvious, it's kind of evident, you know, these are all nice analytic functions. So it doesn't really care about the sign of C either. So it also works for either sign of C. Okay? So although I was phrasing C sort of initially normalized for the 2 to the 3 to 3 amplitude, it would also work when C was negative. Okay? So it's also true when I plug this result to get the out in for the 2 to 4 amplitude. Okay? So what have we concluded? Is that in the lambda phi 4 1 plus 1 theory, the 2 to 4 amplitude at tree level at least is a constant. Okay? Wouldn't be true in more dimensions. Okay? I've done the calculation, it's kind of clear it's not really true. Okay? So it's rather special, it's rather surprising. And people for a while, because in some sense it's a classical result, it's very interesting to notice that actually for a time people were sort of, when computers weren't as powerful as they are now, they even did simulations of classical scattering of various, well in particular kinks in phi-4 theory. That's when you have the wrong sign of the x squared term, it's the same sort of game. And the scattering was surprisingly good. Okay, a surprising little mess came off. People even started to wonder whether secretly the theory might integrable. Of course, when they, in more detailed calculations, they found that it wasn't quite true. But somehow, even non-integrable theories are surprisingly close to integrable theories in 1 plus 1 dimension. Okay, well, having come so far, there's one further thing we can think about, which is that if you think about all the possible diagrams we could draw, we're sort of in the universe of scalar field theories. There's one and only one other diagram, or one other term, one other interaction term, that would give a similar property, actually in a much easier fashion. And that's a phi-6 vertex. Okay, so there is one only one other interaction that would contribute a constant to this 2 to 4 process. Okay. Okay, so an extra term, just add an extra term minus mu over 6 factorial 5 to the 6 is an extra vertex to add to my list, like that. Okay? And that kind of rather obviously just gives me a constant with the same factors of all the lengths as I had before. So now I'm going to decorate my gadget like so. Okay, now that's, we don't need to do any of this faffing around with that, we can just sort of read off straight away what we get. Okay. So the full amplitude would now be, my blackboard control is breaking down. So I've now got my amplitude. So now in my sort of 5, 4 plus 6 theory, it's full amplitude for 2 to 4 is now going to be this constant times I lambda squared over m squared plus same constant times minus I mu. Okay? So you can do the exercises carefully and check that you agree with me. Okay, so now the temptation is kind of irresistible to say, well, let's try setting mu equals to lambda squared over m squared. Yes, please.
Why did the both do the same?
Because it's the only other factors are to do with what's going on in the legs. Okay, so I sort of plug together, you know, say this, and the stuff I haven't worried about is how I'm normalising what's going on here and here. You know, you sort of take that out and you've got the same things inside. Okay, so the only difference is, in this case, I've got 2 phi 4 vertices and a propagator. In this case, I've got a single phi 6 vertex. Okay, and that's kind of, especially because I'm trying to get 0 as the final answer, that's why I'm not really too interested in the constant. Okay, so you can do a safe calculation. So if mu is equal to lambda squared over m squared, then 2 to 4 vanishes. Okay? So now we've got a theory where if we take 2 particles, no matter how hard we hit them against each other, at least at tree level, we never produce 4 particles in the out state, which is not like what you see in CERN. It's not like what a standard quantum field theory would do.
So 3 to 3 is not enough.
Yes.
How comes?
So you're stealing my thunder from the next lecture. So, you know, a keen student was meant to say, hang on a moment at some point, but you're being a keen student. So, no, the problem, okay, so the treat is that 3 to 3 does vanish if I've got generic outgoing momenta. Okay? Remember, I have overall, I'm really saying about 3 things that I wanted to say later, but since I've got little time, I'll say it anyway now. So, in general, our outgoing momenta are not completely fixed by the ingoing momenta and overall momentum conservation. Okay, so in these theories, it turns out that the generic 3 to 3 is still 0. Okay, so here it's still true. But when the outgoing momenta exactly match the incoming momenta, right, which is a kind of character, another bonus feature of an integrable quantum field theory, because that happens, then the leaving out of the I epsilon becomes a serious sin. Okay. So when the outgoing momentum exactly the same as the ingoing momentum, then this guy here is clearly going to be on shell. Okay, and then you're not allowed to leave out the momentum. And what happens is, so that then you have a further subtlety, which is that normally, the reason you can't get the I epsilon is because I epsilon in some sense tells you from which direction you should continue your amplitude. Okay, either above or below, in whatever levels you're using. And it turns out that when you, remember we didn't just have this diagram. If I undid my permutations and all the rest of it, I'd have, how am I going to draw this? I could have a diagram which looks like that, for example, as well. Okay? And if you do the calculation carefully, you'll realise that these different diagrams actually tell you to continue in different directions. Okay, so what's called conflicting I epsilon prescriptions. Okay, so if you do an honest adding up of those diagrams and take that into account, you'll find that when you compute the final amplitude by taking limit with epsilon goes to 0, you'll be looking at this. That sort of identity is going to be needed. Okay, so you'll generate, in perturbation theory, a delta function from this, which exactly gives you non-vanishing for 3 to 3 connected from that. Okay, so that's the long answer to the question. That makes sense. It's quite neat. I mean, so, the standard stuff about analytic, if you read the old book, like Eden, Landshoff, E.L. Olive and Hoppingham, they'll tell you that amplitude should be analytic in the remaining momentum once you've imposed overall momentum conservation. And that's very much not true for exact case matrices. How's it consistent? Well, it's because of this sort of thing. Okay? And in fact, after Elop, there were other people who sort of looked at analytic case matrices even more carefully. These sorts of phenomena were taken into account. So you get these sort of hypersurfaces where we have extra singularities and bits of amplitude which support all these hypersurfaces. Even in general quantum field theory, it's not special critical quantum field theory. The special thing with integrability is that all the bits away from this delta function will cancel completely. Good. Okay. So anyway, that was a little bit of a sneak preview, or just a bit. Okay. Right. So we've now come up with a special Lagrangian here. So I'll put mu is, what's it going to be? Lambda squared over n squared. Now I've got something. And if I'm going to set, let's just set beta squared equals lambda squared over m squared. And there's got my normalization's a bit funny, but anyway. Then L, so exercise to correct the typos. Slightly more suggestive way. Okay, so the same. That looks, you can't quite spot the pattern there, but if you write it down in this way, it may be a little bit more suggestive. Okay? So for this model, 2 to 4 vanishes. So let's continue. And I won't do it, because I.
Could you also make advance at loop level?
Pardon?
So if you go to loops.
You could. I won't. You could.
Could it advance this?
Yes. So the claim is that it does. So there's a calculation by Korapin and perhaps another back from the 70s where they did a one-loop calculation. Okay. But the claim is that however many loops you go to, it should continue to be true. Okay. So the fancy way of doing it now is to.
So it's just this term in the.
No.
Okay. So.
Yeah. Sorry, I didn't understand the question. Yes. Once I've got to the end of this story, then the claim is we'll have something where. Yeah. No. I wouldn't claim. Okay, partly because I don't just want the 2 to 4. So let's continue. So what about 2 to 6? Okay, so again, exercise with a star. Okay, so think about writing down. Now I've got a theory with a 5-4 and a 5-6 vertex. Okay, I can try and write down what the 4 to 4, for example, would be, or maybe you can organise things better by doing ace to 0. I don't know, but anyway, think of it for yourself. Okay, by gluing together all the possible diagrams I can make using my current little stock of vertices, which is that 5-4 and 5-6 vertex with a particular relative normalisation of their two couplings. Okay, those have been settled already by demanding that 2 to 4 should vanish. Okay. But what I claim is that this should give a constant. Okay, I have other other reasons to do with conservation rules for being sure that it will give a constant, but I must confess I haven't done the explicit calculation. Okay, but I suspect there's some nice fancy little identity, a bit like this one I wrote down here, which is making the thing work. So maybe someone can find it. Okay. So if it gives a constant, then I can again get 0. Now, so at the moment I've got a theory where if I take two particles, no matter how hard I scatter them against each other, I'm never going to produce 4 particles. Okay? But in fact, it would be possible to produce 6. Okay? But now, I can add in a phi to the 8th vertex to cancel out that constant. See, if it didn't give a constant, there'd be nothing I could do. Because the only thing I've got left to add about all the higher vertices would be a phi to the 8th vertex. That's only ever going to give me a constant. Okay? But luckily, it does give a constant, I claim. Okay, so this...
But you say no,
not to my knowledge, I mean, I never bothered. So anyway, you being a diligent student will come to me tomorrow with the answer. But so far as I know, but basically there are lots more. This is the kind of bare hands way of doing these things. And there are, once people know the full S matrix of these theories, you know what the full Lagrangian stuff is, they never bother doing this stuff. But I think I would claim that there's interesting. This is a bit what John Bernard was interested in as well, was the idea that there are these sort of amusing little identities and so on hidden behind the mechanics of making this work. Some of the fancy amplitudes game now is all about saying that Feynman diagrams are a very dumb way of doing perturbation theory. And on the other hand, it's quite interesting how a dumb way manages to come up with the right answer. So it's interesting stuff, isn't it? Anyway, that should give a constant. So that's killed by a uniquely, that's an important point, determined phi 8 vertex. Okay, so if this works at all, right, we're going to have no choice by what we add at the level phi, even without doing the calculation, I know that. Okay, because the best that could possibly happen after Matthias has worked all night to produce me the final answer and told me, yes, indeed, it's constant, is a number. And then my phi 8 vertex is going to have to cancel that number out. Okay, so whatever happens, it's going to be uniquely determined. Okay? It might be that that was 0 already, in which case my phi coefficient was forced to be 0. It turns out it's not. Okay? If you want to kill off the 2 to 6 production amplitude, we're going to have a uniquely determined phi 8th term to add here. Okay? And then now we can keep going. Okay? At each stage, right? So if you want to kill off, so continue, etc. At each stage, okay, 2 to n vanishing fixes phi n plus 2 sort of recursively, uniquely. Okay. So the best I can possibly, in the best of all possible worlds, which luckily turns out to be the, well, quote, real world of scattering in 1 plus 1 fictional dimensions, the best that can possibly happen is that I'll have a unique final answer for this. Okay?
But you never tried this like with some kind of
Not personally.
must be.
Well, it's quite messy, and the diagrams proliferate quite badly.
No, I mean, because right now we solve the equation.
Maybe. Yeah, it could be. I can try that. And yeah, if you could show that coming out, that would be quite fun. But I mean, as I say, it's not, from the point of view of people wanting to go further, it's perhaps a little backwater. But I think it's quite interesting to appreciate when there are things that happen. Yeah, maybe that's a good idea. Okay, so we've got to keep on going, perhaps using some clever idea or whatever, but in the end, so claim is that after sort of winding this through, maybe you systematized it and you found some better way of seeing it. So after much work, perhaps infinitely many, unless you figured out how to do this more systematically, you're going to land up with a half d pi squared minus n squared over beta squared times cosh of beta phi minus 1. And if you expand that out to the first few orders, you'll get exactly what I wrote down there. Okay.
Well, also it's very, I mean, from what you say, it's very unclear whether, I mean, there might be many solutions.
No. Now that much I claim I have shown.
Well,
Right? Because at each order I want to kill off. Right? So the best that can possibly happen, when I've worked up to the level I've got, okay, up to 2 to n, or 2 to n minus 2, I've killed off everything. Okay? I then work out 2 to n amplitude. Okay, by adding together all the diagrams I can from the vertices I've found so far. Okay. The best that could give me is constant. Right? If it gives me some function which depends on the rapidity, there's no way I'm going to be able to cancel it. Because the only other other thing I've got by going to a higher order, the only other thing that will contribute at tree level is a phi n plus 2. Yeah, I'm always working with scalar field theory, with a single scalar field with a local potential. Okay. There's a caveat to that, which I'll mention in a moment. That's basically it. Okay? So as I said, yeah, it'd be nice to do that more systematically. Okay? And that is just what's called the Sype-Gordon theory. From the point of view of perturbation theory, we could replace beta by I beta. Diagrams still look the same. What happens is you add in some non-perturbative state, so the solitons, we'll come back to those later, and we get the sine Gordon model. Okay, you know, that cos of beta phi there, which is like the granddaddy or whatever of all integral models, and was the one for which exactating and asymmetrics and so on were first found. So that's an example we'll come back to later. Okay, we might also rederive that as a sort of, by a sort of different conservation law-based route, which will show us in some ways why this one cropped up anyway. Okay, right. So how much longer have I got? Okay, good. So one aside. Any questions so far? Any more questions? Yeah.
There was missing with phi-3 interaction. Would you get something similar? Would you get a similar result about the phi-3 interaction for the beginning? So you see something.
You're exactly anticipating what I'm about to say. So yeah, very good. Okay. So yeah, I cheated a bit. This is exactly the aside I'm about to make. I sort of tried to pull the wool over people's eyes, but failed. Spotted. So the first aside is I was claiming that the answer, if it worked at all, okay, was then unique. Okay, so I started off with just the phi 4 term there, after my free part. Okay, and then I seemed to at least convince myself, and I hope you, that all the terms I needed to add on were uniquely determined. Okay, sort of recursively starting from that. Okay. And they would be unique, even if I can't do the calculation myself explicitly, maybe Matthias can, but even if I can't, I know that whatever I get is going to be uniquely fixed. Okay? But that was only, so the calculation so far assumed no phi cubed term. Right? And then I had a sort of phi to the minus phi symmetry in the whole game, which I could kind of use to kill off all the odd terms. Okay? And so never generated phi to an odd power terms. Okay? Right, so there's no need, and in fact no way to add in such a term. So once I set that to be 0. Right? We say, once I decide the phi cubed term is 0, say I gratuitously add in a phi to the 5th term. Right? Then that will, if I've got 0 phi cubed term, I'll immediately be stuffed, because my 2 to 3 amplitude will now be a constant, not 0, because there's nothing I can cancel that with. Okay. But that still leaves open the possibility to start with a phi cubed term. Okay. So again, the sort of exercise is to explore, if I take L to be a half of d phi squared minus a half m squared phi squared minus 1 over 3 factorial times lambda times phi cubed. try and say, again, I want to kill off, I want to generate my higher order terms in this, so phi 4, phi 5, and so on, by demanding that my production amplitudes vanish at tree line. Right, so to start, right, so the first term, over here, perhaps. First term in my plus dot 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 will be a phi to the fourth term. Okay. And my claim is it's actually minus 1 over 4 factorial times 3 over n squared times lambda squared times 5 to the 4th. Okay, so I'm claiming, and the exercise is to kind of convince yourself that that's true too, that the unique thing I can put there to kill off all my production amplitudes.
Sorry, what's the simplest?
Huh?
It's two.
Okay, so at the moment, I'm ambitious, right? I want to kill off all production amplitudes. 2 into 3, 2 into 4, 2 into 5, whatever. Okay. So, and kill 2 to 3, 2 to 4. Okay, for the previous problem, I didn't have to worry about 2 to 3, because I only had even all the vertices, so 2 to 3, I can never write down such a diagram. Okay, but now I've got a phi cubed vertex, I can. Okay. And to leap ahead, so if I add that to that, then it is actually the start of L is a half d phi squared minus, again, change my normalization slightly, n squared over 6 beta squared times e to the 2 beta phi plus 2 e to the minus beta phi minus 3, with beta is lambda over n squared. Okay, if you expand that out to the first, up to phi fourth terms, you should generate 2 terms that I've got written down now.
Sorry, what's about 2 to 1?
Huh?
2 to 1.
2 to 1? Well, I don't worry about that because that's never going to happen once I conserve momenta. Okay, it's never going to happen for physical momenta. Okay? Yeah, you're right, and with a phi cubed vertex, since I'm not write down, but that's kind of, you don't worry about that. So that's okay. Okay? Good. Okay, and again, for the same arguments I had before, if this works at all, it's fixed. Yes?
Yeah, I was thinking about this question. So you said about the sign-word theory, but we know this is due to this Coleman theorem by master theory model.
Yep.
So I suppose this is valid also for this theory as well.
Yeah, but then you write it, then you start off with a sort of free fermionic theory.
Has anyone done this work?
Not that I know, it'd be more of a mess, wouldn't it? Because you get these bad
Yes,
states.
so
In principle, yeah, maybe.
Because it's interesting because it's this strong weak
Yeah. Actually, of course, you know, maybe even in the case where beta is real, when I'm looking at Seinstrom, there's a strong weak self-duality in some sense, and beta and 1 over beta become equivalent. And that's also, even that case is not uninteresting, should we say. Okay, and this is often called, at least in sort of English universities, the Buller dot Lagrangian. If you're Russian, you might call it the Isogen-Karapin Lagrangian, but both sets of people will be kind of wrong, because it was actually, you can find the equation of motion that it comes in a paper from 1910, okay, which is before anybody cared about solitons or quantum field theory or whatever, by someone called Yaker. paper, Sur une nouvelle classe de surface. Sorry about my French. You might remember that sine Gordon arose in differential geometry of surfaces before it was the same equation basically arose. And the same is true of this thing. Okay, so the equational motion that results from that thing was actually first written down in 1910. And there's a sort of curious, sort of semi-funny story about this, which is that Buller and Dodd's paper, what they were actually trying to do was, it was in the 1970s, it was the early days of looking at classical integrability in field theory. Okay? So since the early 70s, people have known that sine Gordon supported this infinite set of conservation laws. Okay? There was an infinite set of higher conservation laws, depending on higher derivatives of phi and sort of powers of phi and all the rest of it. Okay? And they wanted to search systematically for other theories which had that same property. Okay? So they looked for Lagrangians that looked like basically d phi squared minus some v of phi. Okay? Where they let v unfixed. And I might talk later or set an exercise, so the simplest possible case where you look for a conservation law, essentially the sort of first thing, so higher spin conservation law above the energy momentum tensor. Okay? And if you look for something that's a sort of next possible even spin after the energy momentum tensor, then you find that actually this v of phi has to satisfy the differential equation, which basically gives you the sine Gordon Lagrangian, or perhaps the Liouville Lagrangian, okay, or a free field. But if you relax that and say I'm going to allow myself to go up to a higher spin, it turns out that this Lagrangian also has a sort of blob of extra conservation laws. Okay? But what Buller and Dodd did, they noticed that, so they wrote down a huge great list of possible Lagrangians generated by their sort of rather laborious calculations. And they said, we spotted that this one's a bit special, but we actually have a proof. And they almost said, but this margin is too small to contain it, that this one actually runs out of conservation laws after all about 10 or 15. So actually we don't think it's integrable, even though it's got these extra conservation laws. Okay, but we think it's interesting and it's a bit special. And of course it turned out there must have been a mistake in their calculations, because fairly shortly afterwards people realized, well, in fact it was via a link between this and something called a two-component theory, called the A2-tone field theory. This is all symmetry reduction of that theory, and people found there are infinitely many conservation laws for those, which would descend to an infinite set of conservation laws for this guy. So Buller and Dodd, not only were they not the first, but they also got it wrong. They still got their name on it, so I think they did pretty well. Okay, I'm almost out of time, but I just mentioned very briefly, how might you go about doing this exercise? Well, one thing you could do, which kind of is a little bit reminiscent of some of the recent ideas about amplitudes, is you could say, well, it's a bit too hard to show that the whole amplitude vanishes, but at the very least the amplitude mustn't have any poles in it. Okay? Now, if you draw the final diagram associated with the two, so if I've got my mu, I've got 4 factorial 5 to the 4th, you can draw heaps of final diagrams for this Lagrangian, which do have poles. Okay, here's a simple one associated with 2 to 3 scattering. Okay, so time is now running sideways for some reason. Okay, so I'm just using my phi cubed vertices, and I can draw a final diagram like that and say if these have momenta, what should I want to give them? Like over to 1, 1, and 1, 1, this one, and 1, 1, this one, and so 1 plus delta, 1 over 1 plus delta. Once I fix those momenta, the actually other two momenta are fixed for me, and you can check without too much difficulty that when delta tends to 0, these two propagators have to go on shell. Okay? I'm not showing you it in more detail, but you know that that one, near delta, this goes like something divided by delta squared, okay? Because each of these propagators go on the shell. It's not totally impossible to figure out how. Okay? So, of course, if we want the total amplitude to be 0, there must be a bunch, the only way that can be true is there are a bunch of other diagrams which are also going on shell at the same moment, okay, for those same values of external momenta, which cancel, okay, which also have poles, which cancel. Okay? So you then have to go away and write down, using your phi cubed and phi 6 sorry, phi cubed and phi fourth vertices here, some other diagrams which will also go on shell at this moment. Okay? And then add up the total contribution. You'll find out bits with lambda in it. Okay, this one's got a lambda squared in front of it. Okay, the other ones will have either lambdas or mu's in front of them, depending on which bits you've added together. Okay? And then by imposing that the total residue of this double pole is 0, you'll get a relationship between lambda and mu. And I claim that that relationship is exactly, well, effectively the one that's implied by that formula there. Okay? By requiring that these on-shell diagrams cancel each other out for forbidden processes. Okay? But it's quite sort of, it's a little bit subtle and quite a fun exercise to see how that actually works. Fun. Okay? And then after that, you could think to yourself, well, have I now exhausted all the possibilities for scalar field theories with just a single field of 1 plus 1? And you can convince yourself that actually, you know, so now that's done, starting with the phi to the fourth, starting with the phi cubed. Okay, if I don't have either and start with higher up, I kind of stuff from the beginning again. You can say I start with the phi to the sixth, I'll have a constant amplitude for 2 to 4, and there are no available vertices higher up which could possibly contribute to that tree line. Okay? So I've sort of given you a physics proof of a little sort of uniqueness, or sort of a twofold uniqueness theorem, which says that the only possible scalar field theories, massive scalar field theories in 1 plus 1 dimension with no particle production, which is sort of a little bit like classical integrability, are the sine-Gordon and Muller-Dot models. Okay, which is kind of a slightly non-trivial result. And I think well, Fuller and Dot had known about it before they started their horrible long calculations, they might have saved themselves quite a bit of time by thinking about it in this way. So sometimes a sort of simple-minded physics approach gets you somewhere. And I think, yeah, as I say, I think it's quite interesting to try to systematize all that. Of course, the other thing, which I was going to say today, but maybe I'll save in case I've got time towards the end, is the obvious next question is what happens if I go to more scalar fields? Okay? So what if I don't have just a single scalar field, but a little gang of them, so phi 1, phi 2, or phi 1, phi 2, or phi 3, and so on, and write down the general possible interaction between those in which all fields are massive. Okay? And again, I don't think that program has been fully carried out, but I claim to know, at least I know a set of possible final answers, which are these things called affine total field theories. So these are generalizations of the sine-Gordon or sine-Gordon model, involving more scalar fields with, again, exponential interactions. And these exponential interactions are coded in affine Dinkin diagrams. Okay, so well, maybe next time at the beginning I'll just show quickly a little picture of all the diagrams. But these theories have lots of nice properties, and nowadays actually people are starting to study the non-affine total field theories again. And I suspect that in a few years' time people will study these affine total field theories again as well. But it turns out there are some very simple-minded calculations like this for the series of super. Yes.
Yeah, I missed something. Is it a theorem for the quantum at the quantum level?
Okay, so at the moment I haven't shown you anything of that. Okay? So the claim is going to be that both of these models retain integrability at the quantum level. Okay?
But this is not a classical proof. I mean, you want to be...
Well, I only did stuff at tree level. So in some senses I feel it's got a sort of classical flavour to it. So I think that, you know, I haven't really looked at loops or anything yet, so it's possible all this would break down when I start considering loops. In fact, there are some very interesting subtleties. I don't know whether this is quite the question, but you can prove classical integrability of these two things completely independently of all of this. Okay. For these total theories, so these generalizations to multi-component theories, you can again prove classical integrability, and that was what was done late 70s, I think mid-80s was the last papers on that. Okay. But then when you come to quantize them, it turns out that some of the nice properties start to break down. And for a while, people thought that the quantum integrability, at the quantum level, integrability was broken. Okay, it turns out the final story is more subtle than that, in that actually the theories associated with non-simply laced Dinkin diagrams behave a bit differently from the ones associated with simply laced Dinkin diagrams. And there's sort of curious strong-weak duality, which means that the strong coupling limit of the theory based on one diagram is actually the weak coupling limit of the theory based on another diagram. And once you take all that into account, you can still believe that the theories are quantum integrable, but it's a lot more subtle in the quantum case. So I don't think it's a guarantee. What I've done so far is not a guarantee of quantum integrability, I think. But once you look at loops, so as I say, I mentioned earlier on that in the case of sine-Gordon, there's a one-loop calculation, for example, which again shows this lack of production.
My question was a bit different. I was saying that assuming I have a model and I know that it is classical integrable, you are kind of saying that it guarantees that there will be no particle production at tree level.
Yes, I believe that's true.
This is
feels right. But I think in terms of sort of disentangling it to show what's going on diagram by diagram, these last calculations, I never made that really concrete. But yeah, basically that's the background. Anyway, that's probably a reasonable place to